This is the third lecture for Unit 6, which concerns atoms and their electrons. In this lecture, we look at the modern quantum theory of the atom. In parentheses, it's the hydrogen atom. We start with thinking about one electron. But this theory works for atoms with many electrons. See, the Bohr model was not an ideal model. It could only describe atoms with one electron, which is to say hydrogen, and not helium or the rest of the periodic table. Better theory was obtained by applying a new quantum theory developed in the early 20th century to the atom. According to this new theory, the electron in a hydrogen atom has some function that describes where it's most likely to be. That function is called an orbital, from the orbits and its similarity to orbits that we looked at in the last lecture. The orbital describes the quote-unquote state of the electron, including the energy. The electron is said to be in the orbital. The new quantum theory has 4 quantum numbers, not just one. Each orbital in the hydrogen atom has 4 quantum numbers. N is called the principal quantum numbers, has possible values 1, 2, 3, 4, 5, 6, 7. This N looks a lot the same as the quantum number N, which we looked at last time in the Bohr theory. In a hydrogen atom, N determines the energy. It's still true that E is negative B over N squared, and that as N increases, the average distance from the nucleus increases. So all these features we've seen before are still true for the quantum number N. However, there's also a quantum number L, or sometimes I will write, in italic L to make it recognizable. This is called the secondary or azimuthal quantum number. What does azimuthal mean? You don't need to know for this course. What you do need to know is that it provides information about the shape of the orbital. And remember, the orbital talks about where the electron is likely to be. So this talks about the shape of space occupied by the electron. The possible values of L are 0, 1, 2, etc., up to n minus 1. So the value of L depends on n. Possible L depends on n. So for example, if n equals 1, the lowest possible value of n, L has to be 0. If n is 2, there could be 2 different types of L. L could be 0 or 1. The different possible L values define subshells for a given shell. Shell is determined by the n value. So for example, if n equals 2, it's the second shell. N equals 1 is the first shell. And there are 2 subshells. One for L equals 0, and one for L equals 1. Third quantum number is called m sub L. It's the magnetic quantum number. M sub L is useful to determining how many orbitals are in a subshell. The possible values of m sub L are negative L to L in steps of 1. Let me re-emphasize that. The possible values are negative L to L in steps of 1. So let's look at our examples again. If L is 0, m sub L is 0. If L is 1, m sub L could be negative 1, 0, or 1. The fourth quantum number is n sub s, the spin quantum number. Electrons don't really spin, but in certain experiments behave as if they do. The result is that each electron has two possible spin states with quantum numbers plus 1/2 or minus 1/2. Notice M sub s is independent of the other quantum numbers. In other words, it doesn't depend on L the way M sub L does, and it doesn't depend on N the way L does. Let's go back to thinking about values of L and M sub L for a moment, and N values. Each L value is a subshell and has a letter designation. The letter S means L equals 0, so L equals 0 means it's an S orbital. P means L equals 1, so L equals 1 type orbitals will be P orbitals. And notice that since there are 3 M sub L values, -1, 0, and 1, there will be 3 P orbitals in a P subshell. D means L equals 2, so if L equals 2, we're talking about D type orbitals. And there are 5 orbitals in a D subshell, corresponding to M sub L values -2, -1, 0, 1, 2. F means L equals 3, so we could talk about F-type orbitals. So, for example, we could talk about the 1s subshell, where N equals 1 and L equals 0. L equals 0 means it's an S-type subshell. We could talk about the 4F subshell. Had to correct a typo there. And so on. Now here we represent the table from the textbook. This shows you that for a given L value, what the letter code is, and how many orbitals are in the subshell. L equals 1 is a p-type orbital, has 3 orbitals in the subshell. I just said on the last slide. L equals 2 is a d-type orbital, has 5 orbitals in the subshell. There are 5 orbitals in a d subshell. An L value of 3 means an F-type subshell. There are 7 orbitals in the subshell, corresponding to values of M sub L, -3, -2, -1, 0, 1, 2, 3. That's 7 values. There are 7 orbitals in the subshell. The number of orbitals depends on the value of on the possible values of M sub L. You can always calculate the number of orbitals just by taking 2L plus 1. So for example, a G subshell has 9 orbitals in it, and an H subshell has 11 orbitals in it. And remember, the value of L is supposed to provide information about orbital shape. S orbitals, for example, have a spherical shape. The electron moves inside a sphere. Well, you should imagine the nucleus is at the origin of this sphere. So any S orbital for any shell, 1s, 2s, 3s, will look like a sphere. Now remember, there are 3 p orbitals, because p means L equals 1. Possible values of M sub L are -1, 0, and 1. There are 3 values, and therefore 3 orbitals. These orbitals have dumbbell shapes that the electron is likely to occupy. And they're pointed orthogonal to each other. Usually we call them the X, Y, and Z orbitals. And the lobes are pointed along orthogonal axes. Here I have pictures of all 5 of the possible types of d orbitals. Now these orbitals, the p orbitals in the last picture showed regions of positive and negative sign. Charge, not sign. I mean sign, not charge. These 5 d orbitals in a d subshell have 4 lobes. Here's one with 2 lobes and a sort of a torus of probability around it. Note there are 5 of them because d means L equals 2, and there are 5 m sub L values, -2, -1, 0, 1, 2. Therefore 5 orbitals in the d subshell. Okay, let's try a practice quiz. Very short quiz. What are the in and out values of an electron in a 3D subshell? What are the possible m sub L if L equals 3? Which of the following subshells does not exist? 2p, 1f, or 3s? And explain your answer. Alright. Take a moment to try these. One more question. And which of these sets of 4 quantum numbers is not possible? N equals 4, L equals 2, m sub L is -1, m sub S is +1/2. And then you have values, you have options B, C, and D to examine as well. Right, take a moment to look at those. Then move forward after you've completed the quiz and grade yourself. A 3D subshell has n equals 3 and L equals 2. If L equals 3, the possible values of m sub L are -3, -2, -1, 0, 1, 2, 3. This means there will be 7 orbitals in a subshell with L equals 3, which is an F subshell. Next question was, which of the subshells cannot exist? And the answer is 1F. 1F means n equals 1. F means L equals 3. And if n equals 1, L cannot be 3. In fact, if n equals 1, the only allowed value of L is 0. D, and both letters B and C are bad combinations of quantum numbers. One has m sub L as 3 when L equals 0, and that's not possible. And in C, the values of L and N are the same, and that's not possible. So there are 2 options with bad sets of quantum numbers in D. Alright, this concludes this lecture, a unit on quantum numbers, shells, and subshells. In the next lecture, we will apply all these things to atoms with more than 1 electron.